In this video, we're going to discuss how to use gradient descent in practice. We will do this by answering several questions. Which variant should you use? How should you set hyperparameters such as the batch size, the learning rate, and the number of epochs? And at the end of this video, we will also discuss how to scale your features. Let's start with the variant. My advice is always use mini batch gradient descent. Remember that this variant in each iteration processes k samples at a time. K is called the batch size. So why this variant? Well, if we set k equal to the number of samples in the training set, we obtain batch gradient descent. If we set k equal to 1, we get the SGD algorithm. So SGD and batch are special cases of mini batch gradient descent. Therefore, we can always use mini batch. It is the most general method. Now the remaining question is how to set k. Please take a second to think about this, pause the video, and afterward we discuss the answer. Okay, welcome back. Mini batch can process k samples at a time. Thus, if k is larger, more computations are done in parallel. Therefore, a larger k is more efficient. Furthermore, mini batch averages the gradient of k samples. Therefore, the larger k is, the more reliable the steps are. Because less steps are noisy and wrong, we may need less iterations. Thus, a larger k is usually more efficient. Thus, we want to set k as large as possible. One way to accomplish this is by trial and error. Increase k as much as possible. If you set k too large, Python will crash or throw errors. In that case, reduce k again until gradient descent starts working. This way you can find the largest possible k that works for your problem. Tuning of the other hyperparameters can be done by looking at a training curve. The training curve shows you on the y-axis the objective function, or how good your model is performing, and on the x-axis it shows you the number of epochs. Ideally, your objective function is going down and converges to a good solution. Looking at the training curve on this slide, we can see that the optimization has not yet converged. This means that if we run the optimization longer, the objective function will probably improve significantly. One way to fix this is to increase the number of epochs or to increase the step size eta. Imagine we have increased eta, the step size, and we obtain this training curve. Observe that the objective function is increasing. This is not what we want. The objective should always become smaller. We also say learning is diverging. Why does this happen? Well, remember, the gradient is only locally valid. If the steps we take are too large, the direction we start out with may not be correct anymore. In that case, you will see that the loss increases instead of decreases. Now I've made the learning rate a bit smaller, but still larger than in the first plot. Observe the error is going down and it seems to converge. It looks like no further improvement can be made anymore. In this case, our learning rate seems to be well tuned. The learning rate and the number of epochs are two essential hyperparameters of gradient descent. If you set them wrong, your model will not learn. So tune them with care. Okay, but how to tune them? Remember, the learning rate is always positive. However, it can be as large or as small as possible. There are no clear upper or lower bounds. Therefore, we tune it using a logarithmic scale. This means you first try 0.001, and if that doesn't work, you try 0.01, and then you try 0.1. Then you try 1, 10, 100, etc., etc., etc. This way, we can quickly find a good order of magnitude for the learning rate. Tuning using a linear scale will take too much time. This way of tuning hyperparameters is called grid search, since we set up a grid of parameter values to try. If you find that 0.1 is the best learning rate, you can then search further around that optimum. So you will try 0.1, 0.2, 0.3, etc. until you reach 1. Afterward, we can set up an even finer grid, and you can keep going like this until you're happy with your performance. Like other hyperparameters, it is best to tune it on test data. This means you let the algorithm train all the way and at the end record the performance on a test set. Then you try multiple values for the hyperparameters and you choose the one that performs best on the test data. However, people often also use the training curve for tuning. Why? Well, the training curve is usually made interactively during the training procedure. So we can stop the training directly if we see the loss diverges. Also, we can often see by eye that the loss converges and we can stop training early. Therefore, training curves can help you tune the hyperparameters much faster by hand. Realize that this way of tuning is a bit more heuristic and subjective. But if your optimization is taking an hour or sometimes even days, you will want to use the training curve so you can stop optimization early. This way, tuning can be much faster. Okay, now let's talk about the number of epochs. In an ideal world, you would also tune this on unseen test data. However, it is much faster to look at the training curve to see if the objective has converged. What do I mean by that? Well, if I look at this curve, I would say that this is clearly not converged. The objective is still rapidly decreasing. If I increase the amount of epochs, our result will get much better. This second curve looks more like it has converged. However, be sure to check the scale of the y-axis. Is the mean squared error here really not improving anymore? Okay, so maybe this has converged. To make sure it is converged, we should zoom in on the last part of the curve. Finally, let's talk about feature scaling. Here are two examples. For the left, the two features are on the same scale. For the right image, the two features are on a different scale. For one of these figures, gradient descent converges more easily. Why is this the case? That is a more difficult question. This is your challenge. Pause the video, think about this, and afterward we discuss the answer. Okay, welcome back. The answer is the steps taken in different features are not on the same scale. To the right, you see that the steps in the direction of feature A are very large and the steps in the direction of feature B are much smaller. Because the parameters for one feature make much more progress than the other, gradient descent is going to take a long time to converge. This is why you want to scale your features and to make sure they are on the same scale for gradient descent. This leads to a faster convergence. Let's summarize how to use gradient descent in practice. Always use mini batch with a batch size that is as large as possible. We discussed how to tune the learning rate using a logarithmic grid search, ideally using a test set. In practice, people often look at the training curve, because this way they can stop training early, which can speed up tuning a lot. However, this approach is more heuristic. Ideally, you also tune the number of epochs on a test set, but here often people also look at the training curve to save time. Finally, bringing features to the same scale usually benefits the performance of gradient descent.